Okay, let's unpack this. We are diving deep into, well, maybe the most successful piece of personal defense ever evolved in vertebrates,
Yeah.
the turtle shell.
Yeah, absolutely. I mean, when you think about armor in nature, it goes way back, like over 500 million years, right? To the Cambrian period.
Right, that's when you first see things like shells and exoskeletons popping up.
Exactly. And you get things like, a clam shell made of calcium carbonate they secrete.
Yeah.
Or think about a lobster with that chitin exoskeleton they build chemically.
But that's where turtles, the testudines, just go completely off script, evolutionarily speaking.
Totally. Because their shell isn't something they secrete or build chemically on the outside.
Yeah.
It's different.
It's internal. That's the part that's still, well, it blows my mind. The turtle shell is completely unique among vertebrates. It's fused permanently to their skeleton.
Yeah, fused right to the spine, the ribs. It basically encloses everything vital inside this bony cage.
So it's not like a house they carry around.
No, not at all. It is their body plan. They grow with it. Right from when they hatch, they can never leave it. Ever.
And this basic blueprint, this design, has worked so well, it's barely changed since the time of the dinosaurs.
It's incredible, really, which makes it such a fascinating subject for a deep dive,
Absolutely. That permanence. We're not just looking at armor. It's like a living fortress that's lasted eons. So our mission today, understand the engineering, the diversity, and maybe get into the surprising new ideas about why it even evolved.
Okay, let's start with the basics, the anatomy. You're basically looking at two main bony plates that create this total body armor.
Right. So on top, you got the big dome, the shield part. That's the carapace.
And if you've ever felt one, you know how dense that is.
Seriously solid.
And that comes from its structure. It's built on fused bony plates underneath. But you don't usually see those directly.
Because they're covered by the outer layer, right? The scutes.
Exactly. The scutes are those keratin plates, like scales almost, on top of the bone. They give the shell its look, the color, the texture, the patterns. That's what you actually see.
Okay, so carapace on top with scutes, and then underneath, protecting the soft belly.
That's the plastron. It's usually a smoother plate on the underside.
And the two connect somehow.
Yeah, they're linked by a really strong bony bridge on the sides. It creates that complete 360-degree armored capsule.
Wow. Okay, to really get a feel for this bone armor, let's look at some masters of the hard shell. Maybe start with the biggest one in North America, the alligator snapping turtle.
Oh yeah, that thing is formidable. The shell is just massive, often covered in these huge, spiky, knobby scutes. It honestly looks like something out of prehistory.
I've heard people compare it to Bowser from the video games.
That comparison is pretty apt, actually.
Yeah.
Dark, imposing, ridged. It looks tough.
And apparently the attitude matches the armor. Super defensive, right? With an insane bite force.
Oh yeah. They can reportedly snap clean through a broom handle. It's serious defense. Important though, like you said, North America, we should probably note, it's different from the common snapping turtle.
Right, the common snapper is smaller, but also notoriously, let's say, salty. Also very defensive.
Equally salty, good way to put it. But the alligator snapper relies on that sheer power and that almost impenetrable shell. Now, contrast that approach sheer force with something totally different, like the mata mata from the Amazon.
Oh, the mata mata. Its shell is just bizarre looking. It's all rough, lumpy, kind of like wet tree bark or dead leaves.
Exactly. It's the ultimate camouflage artist. That shell texture and coloration, plus its weird, flat, leafy-looking head, it just vanishes in the shallow, slow-moving, leaf-littered streams and marshes where it lives.
So it becomes invisible, basically.
Pretty much. And unlike the snapper using its shell for brute defense, the mata mata uses its look for hunting.
How does that work?
It sits perfectly still, looking like just another pile of decaying leaves on the bottom. Then, when a small fish or an invertebrate swims close, completely unsuspecting, it snaps. Nope. It doesn't strike. It opens its mouth incredibly fast, creating a sudden vacuum, and just sucks the prey right in. Whoosh. Gone.
That's incredible. Total deception built into its armor.
It really is. And, thinking about these shells, it's worth remembering, this hardcore armor isn't there from day one.
Ah, right. Baby turtles. Their shells are softer, aren't they?
Yeah, more flexible. They haven't fully calcified yet, which actually gives them an advantage the adults lose.
What's that?
Well, if an adult turtle gets flipped onto its back, it's often in big trouble. The shell is too heavy, too rigid. They can't easily right themselves.
Yeah, they look pretty helpless.
But a baby turtle, with that slightly bendier shell, they can usually flip themselves back over much more easily.
Interesting. So that flexibility, that kind of leads us into another big split in the turtle world, right? The hard shells versus the soft shells.
Exactly. It's that classic evolutionary trade-off. Maximum protection versus mobility and flexibility.
So soft-shelled turtles. What's their deal? Like the Asian giant soft-shell turtle, which is sadly endangered.
Right. They basically ditched the bony scutes altogether. Instead of that hard outer layer, their shell is covered in this thick, tough, almost leathery layer of skin or tissue.
So less protection, presumably?
Somewhat less rigid protection, yes. But the payoff is huge. Their shells are way lighter, often more streamlined. That makes them much faster and more agile, especially in the water, but also sometimes on land, too.
Okay, lighter, faster. But the adaptations get even weirder with aquatic soft shells, don't they? I read something about breathing underwater.
Oh, yeah, this is where turtle biology just gets wild. Some aquatic softshells have evolved this incredible ability to essentially breathe underwater for really long periods without using their lungs.
How on earth do they do that?
Well, they basically use other body parts like gills. They can absorb oxygen through tiny, specialized tissue projections in their throats. So kind of breathing through their mouth underwater.
Okay, that's weird enough. But isn't there another way to... Something even stranger.
Yeah. The other way is, well, famous. They absorb oxygen through specialized structures inside their cloaca.
Wait, the cloaca. That's the all-purpose exit for waste and reproduction.
That's the one.
So they are literally breathing through their rear end.
Effectively, yes.
Uh-huh.
Cloacal respiration. And the poster child for this is the Mary River turtle from Australia.
Ah, the one that sometimes gets algae growing on its head and shell? The green-haired turtle.
That's her. She's known for staying underwater for, get this, potentially up to 3 days without needing to surface for air, thanks in large part to that cloacal breathing.
Wow. It's like they thought, okay, the shell's kind of heavy, maybe cumbersome underwater, I know. I'll evolve built-in scuba gear in my butt.
It's an amazing workaround for the whole density issue.
Speaking of density and body plans, we should probably clarify the whole turtle versus tortoise thing, too.
Good point. Generally, we use turtle for species adapted to water. They tend to have more streamlined hydrodynamic shells. Think sea turtles or sliders.
Whereas tortoises are the land dwellers, built for life on solid ground.
Exactly. And their shells often reflect that big, heavy, high-domed shells. Less about cutting through water, more about protection, maybe storing water, supporting their weight on land.
But nature always loves an exception, right? Isn't there a freshwater turtle that acts like a sea turtle?
You're thinking of the pig-nosed turtle, found up in northern Australia and southern New Guinea.
That's the one.
Yeah, it's strictly a freshwater species, lives in rivers and estuaries, but evolutionarily it went full marine style. It's the only freshwater turtle that has evolved proper flippers, like a sea turtle, not just webbed feet.
Wow, so it lives like a sea turtle, too.
Pretty much. Almost entirely aquatic. Only comes ashore briefly for the females to lay eggs. It just shows how adaptable that basic turtle body plan really is. You can tweak it for almost any environment.
Okay, so whether they're high-domed tortoises or streamlined turtles, hard-shelled or soft, the classic defense is always that head tuck, right?
Yeah, pulling the head and limbs into the shell when danger appears, that's the iconic move.
The quick pop-in. But even that's not universal, is it? There's another weird adaptation there.
Right, the side-neck turtles. Some species just physically can't pull their heads straight back in because their necks are simply too long.
Too long to retract, like which ones?
The Roti Island snake-neck turtle from Indonesia is a perfect example. Its neck is ridiculously long, almost as long as its shell. There's no way that's fitting inside.
So what does it do when threatened? Just leave its head hanging out?
Not quite. It has a different strategy. It folds that super long, almost giraffe-like neck sideways, tucking its head along its body right up under the edge of the carapace rim.
Huh. So it sort of hides it along the side.
Exactly. It's a solution, maybe not quite as secure as healing everything up like a box turtle,
Yeah.
but it works for them.
Okay, all this incredible diversity, these amazing defenses, it really brings us to the biggest question, the one people have wondered about for ages. Even Aesop wrote about it. Why? Why did the shell evolve in the first place?
Yeah, for the longest time, the assumption was pretty simple and honestly pretty obvious.
Protection, right, from predators.
Exactly. Seemed like a no-brainer. Why else lug around such a heavy, cumbersome piece of architecture, if not for defense? But then, paleontology threw a major curveball.
Ah, the fossil evidence. This is where it gets really interesting.
It started with the discovery of this ancient ancestor, about 260 million years old, called Unetosaurus.
Unetosaurus. Okay, what was special about it?
Well, when scientists looked closely, they saw the beginnings of the shell. The ribs were already really broad and flat, much more so than in other reptiles. But They weren't fused yet. They weren't forming a complete solid shell.
So it wasn't offering full protection yet.
Likely not comprehensive protection, no, which forced them to ask. If it wasn't primarily for defense at that stage, what was it for?
And what did they come up with?
The hypothesis, which has gained a lot of traction, totally flips the script. They proposed that the initial broadening of those ribs, the very first step towards the shell, might have been for something else entirely. Stability and support for burrowing.
For digging, like reinforcing the body to push through dirt.
Exactly. Think about the forces involved in digging. Having wider, flatter, more robust ribs could provide a more stable base, a stronger anchor for powerful forelimbs used for digging.
Wow. So the shell might have started not as armor, but as like an internal chassis reinforcement for digging.
That's the idea. It completely reframes how we think about early turtles. Maybe they weren't primarily walking tanks from the get-go. Maybe the first steps towards the shell were adaptations for a fossorial, burrowing lifestyle. Defense then became a fantastic secondary benefit as the ribs fused further and the plastron developed.
That changes everything. They weren't necessarily built to fight. Maybe they were built to dig, like heavily armored badgers or something.
It suggests a very different ecological role for those early ancestors. So, the story of how the turtle got its shell, it's still being pieced together. The burrowing hypothesis is powerful, but there's still debate. It shows even ancient familiar structures hold deep mysteries. No single certain answer yet for these walking condo units.
Okay, so the why is still a puzzle, potentially linked to burrowing. But there's another piece of fossil evidence that's really key here, right? A later ancestor.
Yes, absolutely crucial. This is the 220 million year old ancestor, Odontochelys.
Oh, Odontochelys. What did that fossil show us?
Odontochelys had a fully formed, bony plastron, the bottom shell, the belly plate. It was solid, but it had almost no carapace. The upper shell wasn't really developed yet.
No way. So the bottom half evolved first. The belly armor came before the back armor.
That's what the fossil shows. The plastron was there, well developed, while the carapace was still mostly just those broadened ribs, not a fused dome.
That is wild. So the armor was built literally from the ground up, maybe protecting the underside while maybe burrowing. That fits the other theory too.
It certainly seems to support the idea that the underside protection was crucial early on. It's just a fantastic example of how counterintuitive evolution can sometimes be. We see the turtles today as this complete fortress, but the evidence suggests the armor came in stages, starting from below.
So we start thinking ultimate defense and end up with maybe started as digging support and the belly plate came first. Amazing.
Which leaves you with kind of a fun final thought to chew on.
Okay, hit me with it.
Remember that old Ninja Turtles cartoon theme song?
Yeah, of course. Heroes in a half shell.
Well, based on Odontochelys and the fossil record, purely by accident from an evolutionary perspective, they were actually spot on.
The half shell, the plastron, really did come first.
It seems so. Just goes to show, doesn't it? No matter how ancient or familiar an animal like the turtle seems, we are still uncovering secrets about how life built these incredible, enduring designs. There's always more to learn.